Hi, and welcome to today's lesson on logic gates. So today we're going to be looking at logic gates, how they work, the different types of gates, truth tables, Boolean notation, and how we can represent these, and finally looking at combining multiple gates. So before we start, it's important to understand what a logic gate is and how a computer is actually set up. So from previous lessons and knowledge, we all know a computer is a collection of circuits and transistor switches. Now, all a logic gate is a series of transistors connected together, and it has one or multiple outputs, and each output is based on the input or combination of the inputs given. The three main types of gates you need to know about are the AND gate, the OR gate, and the NOT gate. Each type of gate can be represented diagrammatically and in notation, as well as a truth table. So now let's take a look at some of the gates. So the first gate we're going to look at is the AND gate. Now, just like the word "and" suggests in the English language, it means a combination. So if person A and person B needed to be in the room for the light to be on, we need both people there. More specifically, an AND gate, also called a conjunction, uses two inputs to generate an output. So the output is only true if we have both inputs. With the Boolean notation, this is represented as A and B, or as you can see on the slides, A with kind of an arrow symbol pointing upwards and B. Now the AND gate is represented as like a D shape with two lines coming in from the left, that being the input, and then one line coming out on the right, that being the output. As we can see from the diagram over here, we've got A is 1, B is 1, so that means Q must be 1. We can treat 1 as on and 0 as off. Now this alternative example, we've got A is 1, B is 0, so that means Q will be off. On the left-hand side, we've got a truth table representing this. So we've got A and B in the columns, and then finally Q. So when we've got A and B as 0, Q will be 0. So both of them are off. When A is off and B is on, so 0 and 1, Q is also off, giving us a 0. When A is on and B is off, 1 and 0 there, respectively, then Q will be off. Finally, when we have A and B both on, then Q will also be on. So in a very simply put, that is the AND gate. The next one we can look at is OR. Again, just like the word in the English language suggests, OR means, we can have either one. So if A or person B is in the room, the light will be on. You could have both of them, or we could have one of them, whether that's A or B. Now looking at it more specifically, an OR gate uses two inputs to generate one output. The output is true only if either or both of the inputs are true, with a 1. The Boolean notation for this can be represented as A or B, or A, then with a V shape and a B. As we can see from the diagram, we've got both inputs here for A and B. That means Q will be on. Then here we've got only A on, B is off, but Q is on, because again, it's an OR gate. Now with this truth table, as you can see, the only time Q is not on when we don't have both inputs. So A and B is off, Q will be off. And as we can see here, when A is off, B is on, we still have Q turning on. Likewise, when A is on, B is off, then Q is on. And then when we have both, Q will also be on. So that's a simple truth table for the OR gate. Moving on, we now look at the NOT gate. Just like the word NOT means in English, if person A is not in the room, the light will be on. So a NOT gate uses one input to generate one output, but it inverts the input, so we can treat it as an opposite. So the output is true if the input is false, and the output is false if the input is true. The Boolean notation can be represented as not A, or like a sideways L shape, and then A. So as we can see from the diagram, when we've got A is on, that means Q will be off because it's inverting it. And when we've got A is off, Q is on. Very simple truth table here also, because we only need one input. When A is off, Q is on. When A is on, Q is off. We're now going to look at how we can combine logic gates. Logic gates can be combined to form more complex inputs and outputs. These combinations are known as logic circuits. It can use a variety of AND or AND NOT gates which could be used in a combination to get any desired output. So we've got this gate here. D is equal to A and B, and then Q is equal to D and C. Now, what we can do when we're working this out, we've got all our possible combinations here for A, B, and C. But before we can get to Q, we need D, because D is required for Q. So the first thing we're going to do is we're going to calculate what D is when we have A and B. Now, as we know, that'll only ever be true if we have both inputs. So we can fill those ones in, and then the rest will get zeros. Then Q is only ever going to be true when we have D and C. So we don't really need to look at A and B anymore. All we need to look at is these two columns. When do we have D and C? Only here at the bottom when we got both inputs, which will result in Q being on. What I'd always recommend for completing a truth table for one of these circuits is always focus on the right-hand side, what is needed from the right-hand side. Once you understand what's needed from the right-hand side, then you need to ensure that you have that in your truth table before you can get your final output, in this case, Q. And here we have another example, okay, where we've got an OR gate, which is A or B, and that gives us C, and Q is equal to not C. So we have A, B, and C, and then Q in our truth tables. Very simple. We need to calculate C. C would only be true when we have A or B. So we know it's going to be negative when we have neither of them. So that will give us 0 straight away. And then we'll have ones in every other column. And nice and easy, Q is only true when we don't have C. And there's only one instance of that. And that gives us 1 here. And then we've got 3 zeros. So that's an example of another combined logic gate. And today we've been able to look at the uses of logic gates in combination. And we've looked at the background of logic gates, what they represent in being transistor switches. And finally, we've touched on the different gates. Hopefully this lesson has been able to help you. Please like, comment, share, and subscribe, and we'll see you at the next lesson. Thank you very much.